Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, about 4 days ago. It presents a new theoretical framework that uses spectral analysis to prove that when neural networks hit their capacity limits, their internal features inevitably organize into strict geometric structures, rather than staying random. The paper is titled Spectral Superposition, a Theory of Feature Geometry. And as we'll see in the figures later, this theory accurately predicts the emergence of complex shapes within the model's weights, which is a significant step forward for interpretability. Figure 1 illustrates the core motivation using a simple example with two concepts: rock, paper, scissors, and heads, tails. On the left, notice how the model embeds these. The hand game features form a red triangle on a horizontal plane, while the coin toss features lie along a separate vertical axis. Current methods, shown in the middle, simply extract 5 separate vectors, which discards this geometric structure. However, the new spectral approach identifies that the coin features share a rank 1 subspace and the hand features share a rank 2 subspace, allowing the method to recover the distinct geometries shown on the far right. Well, Figure 2 details this geometric arrangement mathematically. The 3D diagram at the top explicitly plots the 5 feature vectors on a unit sphere. Notice how the rock, paper, and scissors vectors, labeled W1 through W3, lie flat on the horizontal plane to form a triangular subspace. In contrast, the heads and tails vectors, W4 and W5, align with the vertical axis, occupying a completely separate dimension. The matrix at the bottom confirms this numerically, showing exactly where the zeros appear to enforce orthogonality between the two independent games. So, while the previous diagrams showed one example, Figure 5 confirms the trend across a massive sweep of 3,200 runs. The histogram plots the utilized capacity as a ratio of the total available rank. Notice how the distribution piles up against the right edge, clustering tightly around the red dashed line at 1.0. The statistics box in the top left reports a mean of roughly 0.999. This confirms a conservation law, where models consistently exhaust their available dimensions, creating the pressure that forces features into those geometric structures. Okay, following the saturation result in Figure 5, Figure 6 tests the theory's main prediction, projective linearity. The vertical axis tracks fit quality, while the horizontal axis measures spectral localization. Looking at the sparsity color bar on the right, a clear pattern emerges. The dark blue points in the top right show that low sparsity features are highly localized and achieve a perfect fit. Conversely, the yellow points on the left indicate that high sparsity features remain more diffuse. Well, Figure 18 makes this abstract difference concrete by visualizing the spectral signatures of two distinct feature types. Panel A on the top left plots a well-behaved feature, which concentrates all its energy on a single eigenvalue, shown by the sharp blue spike. This is the spectral localization the authors predicted. In stark contrast, Panel B on the right reveals a dark matter feature, where the red bars scatter chaotically across the spectrum. Panel C below quantifies this globally, showing that well-behaved features form a low entropy distribution in green, while dark matter features form a high entropy cluster in red. Wrapping up, 2 takeaways stand out. First, neural network features naturally organize into strict geometries rather than random directions. Second, spectral analysis provides the mathematical tools to map these structures, proving that capacity saturation forces features to localize. This suggests interpretability should focus on global geometry, not just individual neurons. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.